Hello everyone, welcome back to another MECH 20 video. Today we'll be covering a problem in energy in 3D. Specifically, we'll be covering an example from section 21.3, example 21-35. Let's read the problem. The 200 kilogram satellite has its center of mass at point G. Its radii of gyration about the z prime, x prime, y prime axes are 300 millimeters and 500 millimeters, respectively. At the instant shown, the satellites rotate about the x prime, y prime, and z prime axes with the angular velocities shown here. And its center of mass G has a velocity of negative 250 I hat plus 200 J hat plus 120 K hat meters per second. Determine the kinetic energy of the satellite at this instant. So a comment I'm going to make about this problem before starting it is that it is not a conservation of energy problem. It's simply asking for the kinetic energy of the satellite at this instant. Now, the reason for that is because, well, in the previous problem on angular momentum, we covered part of it, covered conservation of energy. This problem is testing your knowledge on being able to interpret a problem in 3D. For example, in the case of using the correct kinetic energy equation, this is a very easy trap to fall into when you're not clear on which point of rotation you're taking. For example, if you're taking your point of rotation at O, then you're going to have only rotational kinetic energy. If you're taking it from the center of mass or any point rather, your point G, it's moving, so it has translational kinetic energy as well. And of course, since we're in 3D, we have terms for all three moments of inertia and all three products of inertia. You're dealing with many variables at a time, so it's important to be able to set up a problem in 3D so that if you ever do have to use conservation of energy, you'll be able to do it correctly and you'll be able to understand all the terms that you're working with. So going down the list of notes here, energy is a scalar. We're using dot product. I know cross product has been very popular in this chapter. We've pretty much used it for the last three problems. Not in this case. Energy is a scalar. All of these terms are being dotted. Very different. Yeah, Hg can include all three moments of inertia and all three products of inertia. That's what I was saying before, that Hg, if you unpack all of this, it's quite extensive. And then another way to find I. So whenever you have some form shape like this where you need to find the moment of inertia, usually what you'll get is rotational inertia. And rotational inertia is just the mass multiplied by the radius of gyration squared. And if you notice in the problem, that's given to you right off the bat. So you know, based on the problem, whether or not you have to use that. All right, let's go ahead to solving the problem. So the first thing we're going to do is we're going to find the rotational inertia of x prime, y prime, and z prime. So the mass is 200, and that's multiplied by the radius of gyration at kx prime, which is 0.5 meters. And that is equal to 50 kilograms meters squared. And incidentally, since the radius of gyration of y prime is also equal to 0.5 meters, the rotational inertia of x prime is also equal to the rotational inertia of y prime. Then for z prime, it's just 200 multiplied by 0.3 squared, which is 18 kilograms meters squared. So the next question you should ask yourself is, do I have products of inertia? Let's see. The condition for having all of your products of inertia to be zero is there needs to be at least two planes of symmetry. and that can be determined visually. So if we look here, if we're looking specifically at z prime, x prime, and y prime, if you make a cut in the z prime, y prime axis like that, you will see that the satellite is in fact symmetrical about the z prime, y prime plane because this side is equal to this side. So we know that z prime, y prime is a plane of symmetry. Do we have another one? Yes, we do. It is the x prime, z prime plane for the exact same reason. Therefore, we can write this. Right. So it seems like we have everything that we need. So we're just going to write out our equation. So I'm going to make a small side comment. This is what you're left with from hg dotted with omega when all of your products of inertia are 0. That's what you're left with. That's what this is. So we have all of these values. The angular velocities were already given in the problem. Vg squared, we're given Vg squared in vector form. So let's just make that scalar to the scalar form. So Vg squared is essentially, right, now we have everything we need to solve the problem. So if you do all of that, your final answer should be 37.0 megajoules. So this is a pretty short problem. I hope this was helpful, and thank you for listening.